Okay. All right. So let's start. Okay. So we know that if V omega is a symplectic vector space, then the dimension of V must be even. Okay. And now an alternating bilinear form omega on V is V, an even dimensional vector space of dimension 2n, is symplectic if and only if omega wedge powered n is non-zero. Okay, so let's prove the this lemma. So the forward direction for that, suppose we're given that omega is symplectic, then we have a basis such that omega is a sum of the two forms ei star wedge fi star, right? So what will omega wedge power n be? Well, the omega wedge power n, remember that for two forms, if I take the wedge product of two forms or any number of two forms, the wedge product will be symmetric, right? It won't be skew symmetric. The wedge product will be symmetric on two forms. Yes? Right?
Yes.
Are you there?
Yes.
Yes?
Yes.
So what will omega wedge power n be? Basically, I'll take this summation ei star wedge fi star and wedge it with itself n times. So I will get how many terms? I mean, there will be n power n terms, right? There will be n power n terms, but out of those n power n terms, if any ei star wedge fi star is repeated, then I will get 0, right? If then I'll get 0 because I'll get an ei star wedge and ei star, so that will be 0, right? Yes. So that means the number of terms I'll get from each bracket, I have to choose exactly one, right? So basically, I'll be looking at all permutations of the E1 star wedge, EI star wedge, FI star. And each of those I can rearrange because the wedge product is commutative on two forms. And each of those will give me E1 star wedge, F1 star wedge, E2 star wedge, F2 star wedge, En star wedge, Fn star. And there will be n factorial many such terms, right? Yes?
Yes, sir.
Is this clear? So this is non-zero because this is this E1 F1, E2 F2 up to En Fn. This is a basis. So the wedge of their dual basis will be non-zero. So this is non-zero. Is this clear?
Yes, sir.
Okay. Now, for the converse, we're given that omega wedge power n is non-zero. We have to show that omega is symplectic. So let's suppose omega is not symplectic for the sake of contradiction. Then I can write, we know by the previous lemma, we have a basis where you have some u1 to uk, which is a basis of the kernel of omega. And then I have some E1 to EL and F1 to FL, right? Where L is strictly less than N. So omega I can write as summation I goes from 1 to L, EI star wedge FI star, where L is strictly less than N. So now when I do omega wedge power N, then what will happen? From each, I'll have N brackets. From each bracket, I have to choose one out of L terms. So L is less than N. So by the pigeonhole principle, some EI star wedge FI star will be repeated in each product of N terms, right?
Yes.
Yes?
Yes.
Yes, sir. Yes.
So therefore, this each term will be 0, right? As soon as one of these is repeated, the product will become 0. The wedge product will be 0. So this will be a sum of zeros. So this will be 0. Is this clear? And so that's a contradiction, right? We were assuming omega wedge power n is non-zero. So we're getting that if it's not symplectic, then omega wedge power n is 0. Is this clear?
Yeah.
Yes, sir. Yes.
Okay, all right. Okay. So now we can come to what is a symplectic manifold. So what is a symplectic manifold? So a symplectic form on a manifold is a two-form, a smooth two-form on a manifold M, such that omega is closed. And for each P, TPM with omega P is a symplectic vector space. So at each point P, omega is a non-degenerate alternating form on the tangent space. And the important point is that omega is closed. So d omega is 0. Okay? D omega is 0. Is this clear? So, as we've already said, since omega at each point is symplectic, it induces an isomorphism from the tangent space TPM to the dual space TPM star at each point, right? Yes?
Yes, yes.
Yes, sir.
So now, just like we defined for a Riemannian manifold, we could define the gradient vector field of a smooth function because the inner product gave us an isomorphism from TPM to TPM star. And at each point, if f is a smooth function, df at p, that is an element of TPM star, right? It's a linear function from TPM to R. So using this isomorphism, df at p corresponds to a vector. If you use the Riemannian inner product, then it corresponded to a vector which we call the gradient vector, right? So that was the gradient vector field. Now we have a different kind of isomorphism coming from an alternating non-degenerate bilinear form, but we still have an isomorphism from TPM to TPM star. So given a smooth function f, we look at df at p, that's an element of TPM star. We use this isomorphism to pull it back to get an element of TPM. So that will give us a vector field. This vector field is called the Hamiltonian vector field of the smooth function, okay, with respect to the symplectic form. So the definition is the Hamiltonian vector field x sub h of a smooth function h from M to R. H is called a Hamiltonian function. It's just any smooth function. This is defined by saying that this isomorphism omega p tilde applied to xh of p is equal to dhp in TPM star. Is this clear? Yes?
Yes, sir. Yes.
Okay. And also, omega p of, so this is equivalent to saying that basically this isomorphism is what? It's V maps to omega of V comma dot. So this should be the same thing as DHP of dot. So in other words, omega p of XHP with V should be the same as DHP of V, right? For all V in TPM. Yes?
Yes.
And this is the same as saying that the interior contraction of omega with the Hamiltonian vector field XH, IXH of omega is equal to DH, right? What is the interior?
Yes, yes. Yes, exactly.
It
Yeah.
means you put XH in the first position. So instead of a 2 form, you get a 1 form, right? That should be
Yes.
okay.
Okay.
Fine. And now, so before doing the tangent bundle, let me immediately give you an application of the Cartan formula. So here is a proof of an algebraic proof of the Cartan formula. So the Cartan formula immediately tells us if n omega is a symplectic manifold and h is a smooth function on n, then the Lie derivative of omega with respect to the Hamiltonian vector field xh is 0. Why is this? because LXH of omega is d of IXH omega plus IXH of d omega, right? But now IXH of omega is DH. So this becomes d of DH plus IXH of d omega. Omega is a symplectic form, means omega is a closed two form. So d omega is 0. So this becomes d of DH plus IXH of 0. So first term is 0, second term is 0. So this is 0. Okay. Is this clear?
Yes.
So therefore, what does it say? It tells us that any Hamiltonian vector field, it preserves the flow of any Hamiltonian vector field, preserves the symplectic form, right? It preserves the symplectic form. Yes? Because
Yes.
the Lie derivative is 0. So in particular, if phi t star of omega is omega, then phi t star of omega wedge power n is equal to omega wedge power n. It will preserve the wedge products of omega, right? Yes?
Yes.
And if omega
Yes,
is a
sir.
symplectic form, then at each point P, omega wedge power n at the point P is non-zero. It's a top degree form. So it is a volume form, right? That means a top degree form which is nowhere 0. Yes?
Yes.
So what we get is then that the flow of any Hamiltonian vector field, it preserves the symplectic volume form on the symplectic manifold. So any symplectic manifold, it has a symplectic volume form, omega wedge power n, right? That is a nowhere vanishing top degree form. And the flow of any Hamiltonian vector field will preserve this top degree volume form. It will be volume preserving. Okay, so Hamiltonian flows are always volume preserving. So then if you know like Poincaré recurrence theorem for if you have a compact symplectic manifold, then a Poincaré recurrence theorem will tell you that almost all orbits with respect to the volume form are recurrent. They come back within any arbitrary small neighborhood of the point of almost every point infinitely often. Okay, that's what Poincaré recurrence theorem will tell you. So Hamiltonian flows will be recurrent. The dynamics is very different from gradient flows. You see, because what happens for gradient flows, so n omega is a symplectic manifold if Tpn omega p is symplectic for all p and n, and d omega is 0. Okay. And Hamiltonian vector field of H in C infinity n is XH, a smooth vector field on n, such that IXH of omega is equal to DH, and LXH of omega is D IXH omega plus IXH d omega, which is d of dh plus ixh of 0, which is 0 plus 0, which is 0. So phi t star of omega is omega for all t, phi t flow of xh. So
Sir,
this is also called Liouville's theorem, that the flow of any Hamiltonian vector field preserves the symplectic form. This is
Sir.
called yes.
sir, why is a d of dh is 0? Why are you saying this?
You tell me.
So, why is this? The h is a
H is a function.
function. Oh, yeah. Okay, fine.
It's d squared, right? D squared is 0,
Yeah, yeah. D squared is 0. Yeah, yeah.
right? Because d is the dual of delta, and delta squared is 0. So therefore, delta star squared is 0. So therefore, d
Yes,
squared,
yes, yes. Sorry. Yeah.
right? That's
Yeah, yeah.
d squared is 0, right? So that's okay. So so note that omega wedge power n p is non-zero for all p in n. Little n is equal to half the dimension of n. So omega wedge power n is a volume form. So in particular, any symplectic manifold is orientable, right? Right?
Yes, yes.
Because it has a nowhere vanishing top degree form.
Form.
And phi t star of omega power n is equal to omega power n. So Hamiltonian flows are volume preserving. So if n is compact, then the total volume is finite by compactness. Then almost every orbit is recurrent, right? By Poincaré recurrence theorem. Okay, so if you don't know Poincaré recurrence theorem, then you can look it up. It's a very famous theorem. So let
So
me
is
give you.
this an exact analog as in the situation of the Euclidean space where we were talking about Hamiltonian flows and the Leavitt measure, it was like that recurrent theorem.
Well, I mean, it will be recurrent if the. Let me also say one more thing, that also the Hamiltonian flows preserve the function h, because also note xh of h at p, this is equal to dhp of xhp and dH of anything is equal to omega of XHP with that thing. So this becomes omega of XHP, right? By definition of the Hamiltonian vector field. And
Yes.
omega is alternating, so this is 0, right? So this implies that XH of H is 0. So therefore, this implies that H composed with phi t is equal to H for all t, right?
Right.
So Hamiltonian flows preserve H. So H you think of in physics, it's the energy. So what we've proved here is conservation of energy. You model your physical flow as a Hamiltonian flow, where H is the energy function. And then what we've proved here that H is preserved under the flow means that energy is conserved. So this is conservation of energy. Okay. This little fact here is conservation of energy.
So the even-dimensional basis, say if we break it up as Pi and Qi, we can think of as the usual position vector and the momentum, and then considering the partial derivatives in this vector field sense.
Yeah, but I mean, this is, yeah, in, I mean, the Hamiltonian equations that you see in Rn, those are the Hamiltonian vector fields where the symplectic form is summation dxi wedge dyi, the standard symplectic form on R2n, right? Or dpi wedge dqi, summation
Yeah.
dpi wedge dqi. That there you're taking the standard symplectic form on R2n. Is that clear? Yeah.
Yeah. H is the like the total energy, kinetic energy plus potential energy, and then we're considering those coordinates. Yeah. Right.
Right. So H is preserved by flow of XH. So H is. So you contrast this with a gradient flow. So contrast with gradient flow. There ddt of H of phi t of P, this will be dH at phi t of P of grad H at phi t of P, and dH of anything is inner product with the gradient vector by definition of the gradient vector field. So this will be inner product of grad H at phi t of P. So this will be greater than or equal to 0. So in this case, H is monotone increasing along orbits of gradient flow. Grad H. Is this clear?
Yes.
So just to give you an example how different these look, the gradient flows versus symplectic flow, Hamiltonian flows. For example, you take omega to be the standard symplectic form dx wedge dy on R2, right? And inner product equal to the standard inner product on R2. And then you take H to be the function x squared plus y squared. Okay. So dH at P, so dH at a point xy will be 2x, 2y. Or let me put a half here. So I'll get rid of it. So that we get 2 here. Okay, so what will grad H be? Grad H will be the column. This is a row vector. Grad H will be just the transpose of this, right? This will be just the column vector x, y. Yes?
Yes.
Okay. And how do I get the Hamiltonian vector field? That I get by saying that omega of xh with v is equal to dhv. So, okay, let me put a p here, is equal to dhp of v. So this on the one hand, this is equal to inner product of j xhp with v, and this on the other hand is equal to inner product of grad h p with v, right, for all v in R2, right? Yes. So that implies that jxh is equal to grad hp. Okay, so xh. So in this is a general for any function. It doesn't matter what function you take. In R2, xhp is just the gradient flow. So if I apply j on both sides, I'll get a minus and a j here. So this will be minus j of grad hp. Is this clear? So it's just the gradient flow rotated by 90 degrees clockwise, right? So what is the picture? The gradient flow is the radial vector field looking like this, right? And so this is the orbits of the gradient flow. They go out to infinity. And the energy function is the norm squared that is increasing along the gradient flow, right? Now, what is the Hamiltonian flow? You get by rotating this vector field 90 degrees clockwise, right? Yes?
Yes.
So the Hamiltonian flow will look like this. What happens if you rotate 90 degrees clockwise? What will the orbits be?
Concentric circles.
Right, there'll be concentric circles around the origin, right? Okay, so the Hamiltonian vector field. The Hamiltonian flow will be a flow of rotations, right? Is it clear?
Yes.
So the Hamiltonian flow, you can see it preserves the energy function. It preserves the norm squared, right? It preserves the norm squared. And rotations, they preserve volume, right? They preserve the Euclidean volume. Yes?
Yes.
So
Yes,
the
sir.
Hamiltonian flow is volume preserving. The gradient flow is far from volume preserving, right? Small things here will become very large under the gradient flow, right? So the gradient flow distorts volume a lot. Hamiltonian flows preserve volume, right? Is it clear?
Yes.
Yes.
So these two are very different. And the difference is coming from the fact that the gradient vector field is coming from a symmetric bilinear form duality, and the Hamiltonian vector field is coming from an alternating bilinear form duality, right? Okay.
Yes.
Yeah, so gradient flows are what we call dissipative in dynamics. Where will a gradient flow tend to in infinity? As time tends to infinity, if it tends to a finite limit, that means that grad h has to tend to 0, right? If it's converging, the derivative of the curves, the integral curves should go to 0. So grad h should go to 0, and h is monotone increasing. So they will converge to maxima of the function h, right? The gradient flows will converge to maxima of the function h. And on the other hand, Hamiltonian flows will typically be recurrent on a compact manifold. They won't converge. They'll keep recurring. So something like periodic behavior they'll have, or quasi-periodic behavior. Do you understand? So Hamiltonian flows are conservative, gradient flows are dissipative, right? At least if you look on a compact manifold, gradient flows will converge to maxima of the function, whereas Hamiltonian flows will be recurrent on a compact manifold. Do you understand the difference?
Yes.
Yes?
Yes.
Okay. Okay, good. So, fine. So now let me come to what is the symplectic structure on the tangent bundle, right? What is the symplectic structure on the tangent bundle? So that is easy to define. So actually, let me do it in terms of a linear map J. So remember T theta Tm, we had this canonical decomposition into a horizontal component and a vertical component, right? Yes?
Yes.
Yes, sir.
So, so let me just do this. So now M is a Riemannian manifold. And we want to define a symplectic structure, symplectic form on Tn. So we have, as usual, theta is a point P comma V in Tn. And we have the isomorphism J theta, which is d pi theta K theta from T theta Tm to TPM direct sum TPM. So any tangent vector to Tm xi, it maps to a horizontal component xi h, which is d pi theta of xi, and a vertical component xi v, which is k theta of xi. Okay, yes. And using these horizontal and vertical components, we define what's called the almost complex structure. On Tm. So that is this linear map J theta from T theta Tm to T theta Tm. So we write elements of T theta Tm in terms of their horizontal and vertical components. So I write it as a pair xi h comma xi v. Okay. This maps to, so let me just look in the notes to be sure, minus xi v comma xi h. Okay. So this maps to minus xi v comma xi h. Okay. So note that clearly, if I apply this twice, J theta squared is equal to minus identity. Is this clear?
Yes, sir.
Yeah. Okay. In fact, what is the matrix of J theta with respect to this direct sum decomposition? It is just block diagonal. So what should the matrix be? Xi h is going to, so the first row will be the first component, xi minus xi v. So it's 0 minus identity, right? And then identity 0. Is this clear?
Yes.
Right?
Yes.
So let's just let me end this meeting and we'll come back for just 5 minutes and I'll just tell you what the symplectic form is on TM. Okay, just another 5-10 minutes we'll need. So let me stop this meeting now.